All right, that's a lot louder than I thought. Welcome. Thanks for coming here. If you're in the right spot, this will look familiar to you. Why should you care about WebAssembly? In fact, I'm probably going to name this differently next time I give this talk. This is the first time I'm doing this specific one. Because I'm on the back-end focus, which is somewhat rare in WebAssembly. And we'll talk a little bit more about that. And I'll give you a chance to escape if you don't like it. So I'm Adrian. I'm an open source late bloomer. I was working in tech for about 14 years before I started in open source. And I've been doing like nonstop open source since. I work at Tetrate, who's more known for service mesh stuff. But we're doing a lot of open source work with WebAssembly in and outside of the mesh. And if you like stalking on GitHub, I'm Code from the Crypt there. So the reason I'm giving this presentation is that I work on a WebAssembly runtime for Go applications called wazero, sharing experience with projects that use that, as well as a portability specification for server handlers in WebAssembly. And that gets a little bit into the agenda here. So I'm going to talk about things that I feel are a little bit under-discussed and that will be giving you some information you can't just read from a blog. We'll go through the requisite WebAssembly overview because I imagine a lot of folks would be like me a year ago and not know that much about WebAssembly. But we'll go into specific use cases here, which are sort of non-browser centric. For example, embedding another binary inside of your binary. Another stab at the breaking the monolith type of thing. And also some non-romantic parts about programming in WebAssembly. So that's going to exclude a lot of things because there's actually WebAssembly has a lot of buzz. Certainly it started in the web, so there's a lot of web programming practice. I won't have time to get into that. It's really heavy in the smart contract and Web3 space, as well as edge functions. There's a lot of buzz recently about people talking about, oh, can Docker use WebAssembly instead of container images? And even an attempt to do CGI again. These are really interesting and cool stuff, but there's only 40 minutes in this talk. And you can find information on those. And if you can't, you can ask me and I'll show you how later. So, if you don't like it, I won't take any offense. But otherwise, we're going to go. So let's dive into WebAssembly. And it's a real brief intro. And this is technical. So actually, when I was chatting with Emily about the content, she was like, don't hold back. Like, no one wants you to hold back. So this will be a technical talk. But I'll do my best to help it reach all sorts of folks in case they're not working in the same tech as me. So WebAssembly, you can think of it as sort of like kind of dethroning JavaScript in the browser. So you have the three languages in the browser, JavaScript, CSS, and HTML. And so WebAssembly would allow you to run code that was not transpiled to JavaScript and not really even like JavaScript in the browser. And that's kind of cool. So, and amazingly, all the web browsers support WebAssembly. So the key thing to think about is that this is a virtual machine with a bytecode format. So if you said, like, okay, I'm going to do a better job than JavaScript and also the optimizers that run it at a crypto function, then maybe I would define it in Rust. And then I would use the requisite flags to spit out a file with a .wasm extension. So wasm is WebAssembly module, and people will use that WebAssembly and wasm interchangeably. That's a problem of jargon. Then JavaScript, which is the host favorite language, the host being the web browser in this case, can choose to instantiate that WebAssembly module, which includes your crypto functions. Technically, it would be V8, actually whirring up an instance of it underneath, because that's the WebAssembly runtime in like Chrome, for example. And then at the end of the day, you get a sandbox module with some memory. And so the WebAssembly functions are restricted to only operate on their own memory. So they can't access the host's memory directly and crash it or do weird pointer arithmetic or anything. And so one of the funny things you'll see in WebAssembly programming is that a lot of like copying things into WASM and then invoking functions with the pointers to that memory, which way depends on what the function's doing. So that's an overview of how like WebAssembly works in the browser. And the main thing is that it's yet another virtual machine, and it's a stack-based virtual machine with isolation, notably its own memory. Now we've heard about virtual stack machines before. We've heard about Java, for example. So a common question that I find is usually unanswered is, well, what's the real relationship here between WebAssembly and Java? My take is that they have a lot more in common than they have, apart. Certainly, they're both virtual stack machines with an instruction set architecture. They're not real machines like register machines. They both have features that are governed by some sort of a process. So you have the JCP with JSRs for Java, and then W3C has a working group for WebAssembly where feature proposals reach certain maturity phases, and that's how things affect what you can do. Currently, it's no longer the case that people think too much about Java as far as a browser technology. And it's also conversely the case right now. WebAssembly outside of the browser is fairly niche, and that's why I'm talking about it. There is a lot of bias into the instruction sets, which has some interesting side effects. So WebAssembly has a machine code bias to its instruction set. So there are things like SIMD, which is a way to do like multiple, like multiply or whatever operations in one go. So you can optimize code to do that. Now someone probably around here might say, hey, wait, Java has a JSR for that too. It's not to say that there isn't the ability to do these things in new JSRs in Java. It's just that the bias is there towards the machine WebAssembly first. Conversely, Java's language bias has some interesting things about it. For example, because there are common instructions for things like field access and whatnot, you can share things like garbage collectors and object models and even a standard library across JVM languages, which is not something you can do with WebAssembly. So when you compile something to WebAssembly, it's throwing everything in the box. Garbage collector, if it's a garbage collected language, any standard libraries, so you get sort of like the WebAssembly equivalent of a fetch jar or something like that. So it can be less sharing, and of course there's some work in progress that we may see if we do this presentation next year about some component model that's happening in WebAssembly and how mature that gets. But for this year, I'm not going to talk about it. So the main thing we think about in any VM architecture are things like the host and the guest. What does the host do? What does the guest do? So in the case of WebAssembly, the host is the embedding process. And so it's your application if you are writing an application, or it's a web browser if the web browser is the host. And this is not like sharing a kernel or anything. This is a process level user process. And instead of exposing syscalls like you would with normal code, this would have like functions that the guest can call. So it's at an application layer, the WebAssembly virtual machine, and that's kind of important. But the host's mainly job is to spin up the guests, like many instances if you want, and call functions on it. So if you look at the other side, WebAssembly guest, which is sometimes called WASM or sometimes called a module, depending on who you're talking to, this is the thing that is the what you've compiled. So if you compile your favorite Zig software into WebAssembly, and that WASM file would be the guest. And the guest is in architecture and operating system independent bytecode. Similar to Java, it's not ARC specific, which is nice. And the host, of course, can choose to interpret that, or it can choose to compile it down to machine code. It's up to that, right? And as I mentioned before, each of the instances of these modules have the ability to have a separate memory. And much like MS-DOS, it starts with 64K pages. But it doesn't limit you to 640K, don't worry. But WebAssembly is a 32-bit addressing system, so you can't get like huge either. And WebAssembly guests may require functions from the host. So one of the long-touted things about WebAssembly is it's super secure because it can't do anything, which is basically the best way to make something secure. But the functions that it may require, say if it wanted to log to the JavaScript console, it would have to import a function from the host to do that logging, because it can't actually log directly. You can only do things via host functions. So that's something I'll get into soon. All right, now, how do things decide what's compatible or not? So if we're doing normal like microservices, we'll decide what's compatible based on like some sort of IDL or Swagger or proto service or something like that, right? An API contract between the two sides. And in the case of embedding software, then compilers and components would agree on a application binary interface, an ABI. So that's the function signatures and what's expected on both sides of those. And in the case of WebAssembly, the most common ABI that's used outside of the browser is called WASI, which stands for WebAssembly System Interface. And if you're used to Go, this is like XSys, or if you're used to word POSIX, it's the like FD read, FD write, clock time get, things like that. And it's a subset of these things, which are allowed optionally for the guest to access. And this is needed because most of the time you're programming code, and the code would be expected to do something with println, like it would want to do something. Now, we'll get into details of that in a second, but when you talk about ABI, there are things that you would code because it's at like the application layer, and there are things that you could never reach, which is like how println is implemented by Go. So that's an interesting thing about programming in WebAssembly. And if we look at this from like a host guest perspective, an ABI would kind of have a contract on who's responsible to do what. So in the case of WASI, it says that if you have like a main function, then this is going to end up being translated to a WebAssembly exported function called _start. I don't know if you can see the underscore, but there is one there. And then you also have to export memory, because there's an interesting thing about WebAssembly's function signatures. They're numeric parameters. So there's no string type that you can pass in and out or anything like that. So you have to always say like offset length, offset length, offset length. And then what are you offset lengthing from? It would be something in memory. So you have to share memory with the host. And then in exchange, you get these things like reading arguments or getting access to the pseudo random generator or anything like that. And to be concrete, this is literally the specification for clock time get, which is why things are not always compatible in WebAssembly. Very underspecified, loosey-goosey, but people are like, well, just look at POSIX and figure it out. So I've definitely spent a lot of time like just checking, okay, what does Zig do? What does Rust do? And then you kind of negotiate. But we muddle through somehow. And but the point is that when you hear fancy words like ABI, it could just be simply a markdown document that has some words on it. So that's enough theory. Let's get into some practical examples. So first thing I want to talk about is WebAssembly for reuse. So we really like the idea of reuse in software. And so this could be in a case where you might want to not rewrite something because it's too gnarly and you just don't have time. So all of these examples will be real code on open source on GitHub. And I will, again, share the slides, and they'll have links that you can click on, because it's hard to click on this. So let's talk about safely running a binary inside of yours. There's a Go photo editor called Rethink Raw, which is a neat hobby project. And it's sort of like, I was chatting with the engineer who works on this, and said that, well, why were you using WebAssembly? Well, there's this neat DC raw C app that does like re-rendering of images and into thumbnails and such like that. And it's one of those things where this .c file is like copy pasted around, and it's been for years. But there's some bugs in that, and it will crash the process. Like, I don't want to use like TinyGo even if I could, because it will take down my whole app. And so one of the features there that was sought out was like the safe sandboxing. In that case, that not likely to have this thing blue screen or whatever. And so it happens to be the DC raw is compilable to WebAssembly. Don't make that assumption for all software, because usually there's significant surgery involved in getting that to work. But once it works, then you can use it. And so the interesting thing here is this is a Go application, and you can see that we're actually passing like what look like command line parameters to the thing inside of our function definition. And under the scenes, what happens, and this is using wazero, which is the WebAssembly runtime I work on, it will whir up a module of this thing and then kick off its start function, which is, again, analogous to its main function. And it will start asking for things. Okay, what are the arguments? Like, okay, well, -e -c input. And it's like, oh, input. So where's the file named input? So, and then the Go code has faked out a file with like a isolated file system that could only read one path. And it also, instead of using standard output, has remapped that to like a buffer, so that then it can just return the image. So all of these things are rendezvousing through memory, like I said earlier, because, for example, when you're getting arguments, it actually has to have those written in memory somehow, so that the WebAssembly guest can read them. And similarly, if it's reading a file, it would have to buffer those into memory so that guest can read them. And whatever the guest has written, in this case a thumbnail, has to be read from memory. So basically everything goes through this safe D-box. And this is real world code. It works. You can play with it if you want to. But this gives you the general idea of how the relationship goes. And performance, it really depends on what type of application it is. It could use a lot of memory or very little memory. It could start in microseconds or longer. It really depends on what you're doing. Now let's get into something which I find is also kind of fun, which is like, let's take another look at breaking the monolith. Because sometimes we use microservices because we don't have another way of breaking the monolith. So APIs. Should we do that? We've been told for a decade that we can break up large code bases into smaller code bases and make them more approachable by using things like microservices and maybe 1,000 GitHub repositories. And then, that gets us into some complexity sometimes, which is, and some performance problems sometimes. We may have some weird things going on where we end up using webhooks all over the place and stuff. And some of those cases don't actually need to exit the process. Like, it's not even about performance. It's just like there's no real use case for that to leave the process. And so in these cases, we can talk about maybe using an embedded piece of software instead of remote software to do the same job. And I'll put disclaimers everywhere because I'm definitely not going to try to push anyone into programming WebAssembly. It's a dangerous place. But if you're interested, you can try it, and it will be fun. So now this is going to show like my perfect animation skills in a minute. But if we talk about breaking a monolith, let's say that, okay, we have this thing, and then we have this thing that we decide can be like ousted. So you can decouple it with gRPC or something, or REST, whatever you want, and then you just have some component that calls the other thing, and now you can happily leave that code outside of the monolith, maybe and feel free to change that at a different speed than the monolith it came from. And so those are kind of neat things you can do. You can also do that with WebAssembly ABI as long as you've defined a stable one. So just like in a microservice, you would have to have a stable API. You'd have to have a stable ABI, which is sort of a chicken-egg concern about stability. But and then also there's some services that would allow you to kind of use like protobuf service definition and also use that for WebAssembly, which is nice. Then you can kind of like play around and try before you buy. But watch. Yeah. So the main thing that's different is that the code is still running in the process. And so it's not leaving the process. So in this case, what's different is you don't have like need like 15 layers of circuit breakers and all the other things to access this particular functionality. You just have to be careful about, how much memory and which you can bound, and whether or not you're worried about infinite loops taking down the rest of your things. So let's talk about another type of monolith. We'll go for a CLI. CLIs are very commonly monolithic in nature. It's command line applications. And I'm going to use the word monolith for anything that results in one big old binary. So it doesn't matter to me if this thing has 16,000 Git subrepos that it then pulls in. At the end of the day, it's a monolithic binary. And also I don't care if it's 8 meg monolith or 800. So let's look at Aqua Security, who are here in the boothing place. They have a nice open source software that some people have probably seen before called Trivi, which is a vulnerability and misconfiguration scanner. And that's written in Go. And this is one of those type of use cases that's just screaming for modularity. Because if anything that has site-specific nature, in order to adapt to the needs of a site, you're usually either going for a configuration approach or a DSL or something else to make it customizable and work. Otherwise, you have people doing things like ignoring alerts and not remembering why, or worse, not seeing them because they don't have a way to express those things. If you think about this type of policy, it's analysis of maybe a machine image, and then classification of severity levels of things that it's noticed. And I would say that WebAssembly on the back end is very commonly a partner with policy, whether that's web application firewalls or OPA and other types of policy engines and admission controllers. Anytime you see a place where there's site-specific policy requirements, that's one of those places where you might find WebAssembly living around. And the main challenges of a CLI that lead people to monolithic builds are because of the way that releasing works. You have dimensions of operating systems, and now of course you have each operating system having multiple architectures that are even routine and common. How many people have run into a problem when they got their M1? And then you have layers of things on top of that, like you have Docker, and maybe you have repackages in a GitHub action and all sorts of things. So you don't want to add so many different flavors of your binary because it just explodes all these things. And that creates some tension, which is very similar to normal monolithic service tension, which is there's pressure, there's gatekeeping maybe about oh, this is not so nice, maybe we don't want this in there yet, or maybe you have to do your custom build. And certainly things like policy are very much like the if statements that maybe not everybody cares for. So WebAssembly is an interesting way to do things like decoupling policy, and Trivi is an example of that in practice. It's on, it's available now in the current builds of it. And what they've taken for WebAssembly is actually not making it so much a WebAssembly approach, but to say this is a way to modularize a Go application. It happens to use WebAssembly. So for example, their SDK is actually Go, TinyGo, which is a flavor of Go. And they do use WebAssembly, and they talk about it like that, but mainly it's just to safely extend a Go application. Because there are other ways to extend Go applications, but they have implications like have to install new things on the operating system or whatever. And so in this case, let's say you have, like I'm at the Acme company, and I have a different idea of how severe certain CVEs are for me. Maybe I don't actually think these specific ones are because I have special knowledge about my image, and I prefer to write policy code instead of just tell people, trust me, ignore that one. So you compile that down, and then you can either put it on the file system yourself, or you can use OCI repository, which is like a fancy file server. And then in this case, sorry, it's probably hard to see, this is just saying trivi module install with a remote path to that thing. And then when it runs against like Acme's base layer image, it can go through the normal vulnerability scanners, and then maybe that custom code would reclassify some of the severity levels, or maybe add in a new security check that's required because this specific site has more requirements than another one. And that's a fairly common distribution approach too. So like there are other things on the back end that use WebAssembly, and they often use OCI repositories, mainly because of they're already using them, and there's tagging versions and stuff. So that's one way. Another type of monolith is these sidecars that we see like everywhere in cloud native architecture. So WebAssembly is a nice way to get at deeply embedded infrastructure, things that are really hard to change. And you could even think of it as it becomes more popular in cloud services themselves. They're not likely to run your code natively because you could crash the cloud. But if it's a sandbox WebAssembly, then they might be less worried about that. So sidecars are monolithic also, and highly customizable, but usually a monolithic build process, which are tricky to change not just because of that, but also because there's deep coupling. So for example, if you were to look at Istio, its default build of Envoy is not really like, it's like a tag of another thing, and then so you'd have to really know a whole bunch of things and then churn your computer for an hour building it. There are other ways to customize sidecars without using WebAssembly. Like for example, Envoy has Lua filters. It also has native plugin support. Dapper's another sidecar, which is an event-driven architecture and also has some sidecar nature to it. They don't want any system dependencies, like no libc needing to be installed on the host operating system. They want a static binary. So in some cases, people were doing extensions with like remote services just to customize a few things, which is a little bit nasty if you think about it. So it's an interesting way to sort of solve that. But let's walk into it. So if you take a very simplistic view of sidecars, you have your application and you've offloaded some responsibility to another process to do things for you. Let's say it's OAuth or it's MTLS or whatever. And so this thing is actually handling the traffic into your app, and then like after it's decided things are all hunky-dory, your app eventually gets that traffic. But you want to break the monolith, not because you just have an idea that I just want to go around breaking monoliths, but you've noticed some tension, like there's a feature that you want, but you can't change it, or you can't change it exactly how you want to change it. So for example, I want the first filter in line that's not in my code base anymore to do something different that my site needs. And when everything was in my code, I could just change my code. And now this thing is taking responsibility from me, and I can't really do what I want to do. So I want to own more of the code, not just configuration. So the way that sidecars deal with this is that they define the ABI, or basically the type of functions that they will support. Dapper, the emerging version 1.10, is running a new spec that I work on called HTTP WASM. It will also allow people to use WASI for limited purposes, though it doesn't require it. And what that means is that any of your middleware that's compiled down with these things in mind do not have to change at exactly the same rate as a sidecar, which is nice, meaning that you have the decoupling, and then between versions of your infrastructure, your code would work. And how that works in general, let's take the case of the HTTP WASM API, which you can blame me for the website polish, but I think it's actually pretty polished. Is that this is normal middleware, which means you're going in and you're getting requests, like something handles it and it decides to either break the chain or continue. And the host-guest relationship in middleware is that the host is providing access to the HTTP properties. So like the incoming request body or its headers or whatever, and the guest is asking if it needs to for each of these things as it goes about the process of deciding what to do with the request. And for this particular thing, we have a couple implementations. And so Dapper is using the Go implementation because it's written in Go. And the way it looks, which is a little bit different, is now you can configure the path to the WebAssembly filter, and you can still use your existing filters that are built into Dapper itself, so you can reorganize the chain however you like. But the cool thing is that now you get to own that part of sort of like the edge policy. And that's neat because it's actually even a little bit better than your first thing that you had, because before you could change your app, right? But it might be tricky to make the change for all apps. So in this case, you actually own code that could either be app specific or it could apply to all of your apps. And then you own that, and that's independent of, say, Dapper's code base. So that's kind of neat. Now let's get into the perils of programming WASM. And my general advice would be stick to pre-built binaries or SDKs as long as you can, unless you just want to do some hobby work. Because there's basically 3 ways to get WebAssembly. You can download a pre-built binary that someone painstakingly got to build. You can compile your own with an SDK, which is what I think is a great idea. And the reason is that whoever's made that SDK has already gone through some efforts to like figure out what versions of what work with it and dodge all of the hard parts and kind of like pave a path for you to ideally succeed in. And then you can just go, all right, I'm going to do everything myself. So let's take a look at the 2 and 3. So let's say you're using Go, or really TinyGo, because Go doesn't really work well with WebAssembly. Some things that you'll notice that are a little bit different, and I'll just read them out explicitly because I can see I didn't choose colors very well. But one thing you'll notice is that a lot of times when you're writing WebAssembly code is that you have state that looks a lot more global than it normally should. And that can be scary. You might see some configuration happening in main or like global variables used. But remember that some of these things are only living for a single request. So it's not like a normal program. They can live longer, but it's quite frequently the case that they're just word up for one request and killed. So in that regard, it may feel uncomfortable, but it's not terribly abnormal either. The other thing is you'll find sometimes is that this says request and response. You might find the types not being exactly the same as the standard libraries. And that's either because the standard libraries don't really work well with WebAssembly, or that they're too expensive to implement with WebAssembly. Because you, for example, in our SDK that we made for TinyGo, we decided to, like Go has, I forget which one, I think the request is actually struct and the response is an interface. And so the one that's not an interface is kind of hard to extend naturally. So we just made them both interfaces. And then the other thing that you'll find is like crazy flags. Like I remember from like these like black T-shirt old Java classes with the person who knew all the flags to make the GC work. And it's because there's some weird things about WebAssembly. But fundamentally, usually you're having to choose a target, which is either like pure WASM, like, or a WASI variant of it. And the WASI variant would do things like help your compiler implement panic or throwing an exception into nowhere because it would require usually writing to console or exit code 1 or something like that. And of course, when these exit, they don't really exit your process. They just exit that instance of the virtual machine. And then you may find some other weird things like no scheduler. So WebAssembly has no means to do parallel programming. So that's a funny thing, right? So that means that scheduling code is limited to like coroutines and things like that, which don't have to use multiple threads to work. In any case, the takeaway here is it's a little bit weird, right? And so using SDKs are nice because they typically have examples, and you can mess around with them and figure it out. If you're going manual, let's go with like the most manual language, Rust. You could also be very manual in other languages, but let's just do that. So here you'll see like the impedance mismatch with normal programming, where you would use things like strings and such. You may find that you have to coerce something to like a pointer in length more often. Now the Rust compiler will do some of this for you. I'm making it a little bit more obvious than sometimes it is in practice. And you'll see things like weird like extern C, because the type of things that allow WebAssembly integration are usually the same hooks that allow you to use like native libraries. So if things like JNI or CGO or extern C, like you'll see things like that, which are the same compiler hooks used for WebAssembly. It's just not using C to do it. You could actually put a different letter there if you wanted. The main thing that they need to know about is what they're importing from the host. So if we remember in our thing, the host can allow the guest to import functions, and there's a two-part namespace. There's a module name and then a function name. So in this case, the like junk bin of WebAssembly is env. Like everyone has a junk bin, right? So it's kind of related to JavaScript, but basically the env is the name that people use when they can't think of a better name. So you'll find oftentimes it's very reused. Like people will put all sorts of stuff inside of env. Env log is a very common thing you'll find. And so in these cases, that's sort of like what the manual code might look like for importing a function. And since we have Rust on the screen, I might as well tell you the compilation stuff, which again, I'm going to have to read out because of my bad choices. But the main thing is that like cdynlib is and I'm sure someone here can correct my pronunciation because I'm not a Rastafarian. But anyway, cdynlib is the way that you have to create your software if it wants to result in a WASM file. And then you have to choose which triple you want. So in this case, it's wasm32 unknown, which is for standalone, meaning not importing anything else, just pure wasm or die. And alternatively, it could also have like a WASI as a part of that dimension too. So I hope that I've relayed that programming is trickier. Because I found a lot of like overly romantic WebAssembly presentations, and they don't tell you a lot of this stuff. Not trying to scare you, but trying to give you some caution to your optimism. There's a lot of things that also won't work, and you won't know till runtime. So reflection is a very frequently used feature in Go as much as Java and other languages to implement things like object binding, like a JSON struct, and mapping that to actual JSON will be reflection. Sometimes those type of things don't work, and you'll find SDKs like going around it or using a stream parsing approach or something. I mentioned lack of parallelism that can hit you in interesting ways, because a lot of times people who are working with garbage collected languages are relying on garbage collection being async. And so as you're like running around your function, you may find that GC is stealing work from you to the point where some performance people would just do like what's called leaking GC, which is it never collects at all and just lets it pile up because they're only using it for a request anyway. And then, while I mentioned at the beginning, because there's no standard library, the WASM binaries can be very big. You'll see a lot of romantic presentations where people will say microseconds, near negative speed, and like better than containers. And then simultaneously, you'll find a hello world that's 80 megabytes. And so that doesn't mean all hello worlds need to be 80 megabytes, but you may find yourself paying more attention to build flags and things than you would normally do, because the inputs don't really make sense with the outs sometimes. So, and let's not forget that if you're solely here for polyglot, this is certainly not the only way to do it. There should be someone saying, GraalVM, you know, we can get all of these languages and also web languages and anything else, and that's very true. And even if you were using a like Go, there's CGO and other ways. Of course, there's trade-offs to it. The thing that people like about WebAssembly is because because it was made for the browser, it has some neat security features to it, the sandboxing and whatnot, which help. You don't have as much install base, and then you don't have to worry about it. Looking at data it shouldn't be looking at. Anyway, that's all. I have some things maybe are the ones to take away, but you can take away whatever you like. The main thing I think about is, from a backend perspective, is that I like the idea of being able to extend things safely and without necessarily using RPC to do it. I like the two-way relationship with embedding, that both I can embed the software somebody else made, and maybe they weren't even thinking for it to ever be used this way, as well as being able to have a chance for somebody's private code base to embed my software. And that's kind of a thing that would not normally happen. I've been on repeat about this, but definitely look for SDKs. And also keep in mind that if you see a WebAssembly presentation, it should be different a year later, because WebAssembly is a very fast evolving specification. For example, they have a 2.0 draft, which is incomplete. There's some implications of what happens inside of there, and the practice and tooling and whatever you would think could be standard practice will be different next year. So invite me back. But anyway, if you want some other things, I have some presentations. I'll just read it. Wasmer Things, which is a really neat presentation with a great title by Eduardo Vacci, which goes into really neat depth of a whole bunch of things, including LLVM and stuff. And then my partner in crime, Takeshi Yoneda, who talks about like FFI and the relationship of foreign functions, how you would do it with like normal C versus WebAssembly. But here we are. I don't know if we have questions. I'm already 2 minutes beyond. But if you need to ask me anything, come on up. And thanks for spending time with me.